So previously I actually stopped here and call you to check it out yourself. But now I may have some understanding when we are talking about SI units. Okay. Although this dx over 2 it's a little abstract still. So yeah. If you were to take a look in terms of the meter per second, okay. U itself is meter per second, right? So we write right here, meter per second plus partial U over partial X. Okay, it is simply 1 over S, right? Because meter over S divided by meter. Okay, this is meter and this is meter over S. So if you were to switch it out, you eventually get 1 over S, right? And then multiply by meter, which is, dx over 2. It's some x over 2, right? So you can, as you can see, this portion of it describe the x itself, while this portion of it describes the time it moved from this point to this point. Okay, so this is the very raw concept. Okay, although I can't use this thing to explain, but when you're talking about SI unit, you can simply see where is it coming. Okay, so this is just a change across certain time. That's all we are talking about. Okay, so I hope I let you understand a few of it, although it is simply a little tough to understand. So with this concept, trying to decompose this portion over here to this portion over here, the density is also using this method. Okay, the density is also using this method. Okay, so maybe wondering what am I trying to do with mass? I mean, what I'm trying to do with velocity and density. Okay, we are trying to derive a formula for mass flow rate, okay, where density times velocity times area equals to something. So we are talking about this. So this is the velocity, and this is the density. So the density can be also explained in whatever I explained earlier. So I'm not going to go through this. It's just simply doing some Taylor series concept. Maybe in the future I can do some videos to explain this more clearer. But for now, let's continue. So this mass flow rate, as you can see, is taking density times velocity times area, where this is the velocity, right? So this velocity is actually over here. Okay, it's over here, right? It's the same thing. So maybe I should write it down in a more clearer way. So this whole thing describe this portion over here. This is the density; they are the same. This whole thing describes the velocity. They are the same. I didn't change the filling. While across dy dz, because you're talking about there's a dz and this is a dy, right? You're talking about this interface, this area over here. So this is why this is the area itself. I hope I didn't confuse you. So if you were to expand this thing into this, you'll have this. Okay, this density has this portion over here, and velocity has this portion over here. They are the same. Then now you have to do some multiplication. Okay, so maybe I should hold on a while. We should do together. So rho times u, you have rho u. Okay, and then rho times dx square, you have rho dx over 2 partial u partial x plus dx over 2 u. If you wonder what I'm doing, I'm just trying to solve this thing. This is simply a plus b multiplied by a plus b type of thing, I mean a plus c or maybe b plus c. So this is what I'm doing right now. So and then plus, so we have this thing multiplied by u, so we have u over here, and this dude is a little heavy. So dx squared over 4 partial u partial rho and then partial x squared. It's a pretty much tough stuff. And then this whole thing multiplied by dy dz. Okay. The purpose of me doing this is trying to derive myself with this thing, so that maybe in a test in the future, maybe I'll get more What better is it? So if we expand this thing, okay, so hold on a while. Before I multiply this in to complicate things more, I should simplify this whole thing first, okay? So maybe I should simplify this part. So maybe what is the common term over here? You actually see that dx over 2 are the common terms, right? So I just cube away all this dx over 2. So maybe I just bring the dx over 2 out. So you have rho partial y partial x plus u partial rho partial x plus partial x over 2 partial u partial rho partial x squared. So we have some stuffs over here. They are about the same. So I just flush out all the partial x. So we have maybe 2 partial x. Maybe, sorry. So maybe I should write this. Hold on a while. Okay, so after thinking about it, I actually can do it. We do it. We so-called factorize out of the dx over 2. Okay, we factorize out the dx over 2. We have this, and then we can actually cancel off this portion over here. You can see this is the third order type of thing. Okay, so what I mean is that this partial, say, okay, maybe I should write it in terms of. So this dx is very small. Okay, very small times very small times very small. It's maybe we can call it very small cube. Okay, and divided by very small square. Okay, this partial x is very small. You have something that is very small. Okay, so if it's very small, we can straight away cancel all these things. Okay, we can ignore the space over here. So you may wonder why don't you take very small divided by very small. I mean, why don't you cancel this? Because very small divided by very small, you can get some values, right? Maybe 1, maybe some. So yeah. So this is the only concept that I can, squeeze out in order to derive the stuff. Okay. So eventually, we can actually cancel off all these parts over here, right? Yeah. So therefore, we are left with these things. So let me rewrite again. So after rewrite, you can see this portion over here is being written over here, and then this is also written over here. Okay, whatever things that have changed, I just cancel always these things. Okay, you eventually have this thing over here, and then now you can multiply in the dy dz. So you have rho u dy dz plus half in this case, because later in the back we'll just put in the dx dy dz. So maybe I should copy this thing so I will not do any manipulation. So this portion I'll just copy and paste here, and then this dx I'll just move behind. Okay, and we have some we have the dy dz multiplied in. So this is the dy dz. So this is dy and dz over here also. So if you were to check, we have derived the equation for the formula, the mass flow rate across this R plane. Okay, so we have derived the mass flow rate across this R plane. So what about L in this case? What about L? Okay, the whole system is the same. Okay, the whole derivations is the same. It's the same setup, I would say. So maybe hold on. Never mind. I'll just leave it to you to if you are free, just go and check it out. Okay, as an exercise. So nonetheless, we have cleared away this portion over here. We have derived the mass flow rate on the surface R. So the bottom over here is just deriving the mass flow rate across this L. Since we can derive R, I believe you can derive L itself. So I'll just clear off this video, and then I'll just clear off this section. So next video we'll talk about how to derive the rest of the equation. So I'll see you in the next video.